当同时回溯把这个传导相当于上面这就这样的解释，它有时间回溯从哪？不可能，你这样考这个叫。你要先把这样变成你先把数学讲出来。你在第二关键的你总得先把这个数给接上。如果最坏情况是最后才最坏的情况下，最坏的情况这三个在最下面，总把前面给跑起来了。那么前面那方面第二关就是表现。
Right. So today we will do, we'll cover two fun problems in greedy algorithms. One is interval scheduling or task scheduling that we started last time, and the other is Huffman codes. Both of these are just two of many examples that can be solved very well using the greedy algorithm paradigm. We will go on to study other examples of greedy algorithm paradigms. Most notably, we will spend some time talking about minimum spanning trees on graphs, and we'll also spend time talking about shortest paths in weighted graphs. We have understood what minimum hop paths, shortest hop paths are using breadth first search. Then we'll talk about shortest paths in weighted graphs. So just some logistics. We have a quiz 2 on Friday. This will be entirely on graphs, graph representations, and graph traversals. It doesn't cover greedy algorithms. So the problem set, recitation from last week, as well as the recitation from this week would be good practice for a quiz. Yes?
So you put the recitation on Blackboard, because the recitation from last week is not on there.
It was posted, as far as I just saw an email saying.
How about this week?
Well, forget the numbering because we had a review session. So maybe, so I think the one from last week was posted. Has been posted. If not, we will make sure it's posted. Any other questions? Yes?
Will this week's presentation be posted before Friday, this week?
Yes. Any other questions? Yes?
So you brought a big box to class today.
Yes. So I'll be returning the results.
It's present. Should we be worried or like not so worried?
No, there is nothing to worry about. There are so many things, more important things in life than midterms. Okay. So, okay, good. So, let's talk about interval scheduling. So here is the problem is pretty straightforward. You're given, it's very cleanly defined, you're given a set of intervals. Think of these as time intervals. And so think of these as time intervals. Basically, what you're given is timeline, and you're given a bunch of intervals, and the goal to determine maximum number of non-overlapping. Okay? And last time we were just playing around with this, and one idea was that it seems like since every interval has the same value, it's just every interval gives us sort of the same value, why don't we focus on small intervals as opposed to big intervals? And that's a good heuristic, except that heuristic does not always work. And I think we even thought about this. So the simplest example would be, you can imagine there is this interval, maybe a big interval, there's another big interval, and then there is this small interval. Okay? This is the only input. What is the optimal thing to do? Take the two big intervals. But once you take the small interval, you're stuck. You cannot pick any of the big intervals. So the objective, if you pick two big intervals, would be 2. You get 2 of them. If you pick the small interval, you only get 1 of them. So the thing that you're returning is not optimal. Okay? Is that a good algorithm? It's an algorithm, but it doesn't solve the problem that we want. Okay? In some situations, it might be a reasonable thing to do. But for our purposes of this problem, we really want to solve it optimally. We want to find and be able to argue that we are returning the maximum possible number of intervals. Okay? Yes?
Do we know all the intervals?
Yes. So we are given all the intervals at the beginning. That's a very good question. These are not arriving over time. So that's a different model. We are not going to study that model for the most part in this course. So in this model, all the intervals are given to you in advance. Okay. So how are the intervals specified? You can assume that you're given for each interval a start time and a finish time. So maybe the way to think of it is, let's say if I is an interval, you're given Si equals start time and Fi. Okay? Good. So how do we go about attacking this? So when you're faced with a problem such as this, it's good to think of heuristics and play around with examples. That's good, but it's also good to try to understand what would an optimal solution look like. Okay. You may be tempted, actually, so given some other heuristic would be, why don't we try all possible ways of picking overlapping intervals? It's not that hard to see that those brute force techniques would be very inefficient, because the number of different ways in selecting these intervals, you can select a bunch of different intervals. There are really 2 to the n possible. If there are n intervals, there are 2 to the n possible subsets. You can't just enumerate all of them and try. So that's out of question. So you have to do something that understands what it means for it to be a maximum number of non-overlapping intervals. So, and that's one of the things you have to do when you're trying to apply the algorithms, is first you have to try to understand the structure of the optimal solution. Okay? What does an optimal solution look like? And if you can identify within the optimal solution some piece that you think, if you can identify some piece of the optimal solution by just looking at the input given now, then you can make the choice right now. And that's the kind of greedy, that is what's called a greedy choice. in a greedy algorithm, you identify the structure of the optimal solution and identify some choice from the optimal solution that we can use right now. And then you reduce the problem. Okay? So let's try to understand what can we say about the optimal solution. Let's suppose let's try to reason about the solution. Let's suppose I told you that this is in the optimal solution. This particular interval is in the optimal solution. Okay? Can you reduce your problem now to a smaller problem?
Yes.
How? Yeah.
You eliminate anything that overlaps with that piece that is
Okay.
the optimal one.
And then you could argue that the remaining problem is the problem obtained by eliminating these. Why is that? Even though almost it's intuitively obvious, let's try to understand why this statement is there. So let's say this instance is called I. Okay? Let this interval be interval A. And let this interval be interval B. Okay? So suppose I told you A belongs to the optimal solution for I. Let's say A belongs to the optimal solution for I. Suppose. Okay? Then can you describe, so what is the remaining problem that you want to solve? I minus A and B, right? So you would say, so I want to say something like this. Of I then is the same as you take A and then you solve what problem? I minus. So everybody happy with that? Okay. Why is this? Why is this statement true? Okay, so the way we would prove this statement is, okay, opt of I is equal to A union opt of I minus A. Okay. So why are we saying this? So let's say, suppose of I was not I'm belaboring this point even though it's a very simple point. Suppose opt I, I'm just going to prove it by contradiction. Suppose opt I was not the same as A union opt of I minus AB. Well, then, so we know that A belongs to opt I. We know A belongs to opt I. Okay. So we know that opt I minus A is a valid solution for instance I minus AB I minus AB. is opt of okay. So if we have A with opt you get a bigger solution. So if opt I was not the same as this, okay, opt I was, we know that opt I was A and something, but opt I minus A is a valid solution for instance I minus AB. These two imply that the size of opt I is at most 1 plus size of so if we add, we get, instead of saying bigger, I should say at least as big solution of I then R. Okay, so this is an argument which basically is referred to as a exchange argument. So if you say that the remaining problem, if you're not going to solve the remaining problem optimally, then the solution that I will have for opt would be not right, because if solving the remaining problem optimally and adding A will give me at least as good a solution, even better path perhaps, than what I'm claiming to be opt. Okay. In general, you don't have to write these arguments like this, especially for a simple observation like here. The point that's being made here is if you identify a part of the optimal, then it reduces your problem to something else which you can solve optimally. Okay? Okay, so that's a good step. If we knew that this was part of the optimal, then you could take it and then reduce your problem and do it just iteratively. But this may or may not be part of the optimal, we have no idea. Okay? And by the way, there is no reason, similarly, let me ask you one other thing. There is no particular reason why that statement can only be true for the first interval that you see. If you have an interval, set of intervals like these, and I told you that this is part of the optimal, what does the remaining problem look like? It's the same thing. You would take out A, you would take out everything that overlaps with A, and the remaining has to be solved optimally. There is no reason not to solve the remaining problem. Okay? All right. So once we can identify one element, one interval, we can move on. So the greedy all greedy algorithms problems are of the form where can you identify something from the optimal that I can extract and then reduce the problem. Okay. So the greedy, that's what's called sometimes called the greedy choice. What greedy choice can I make? We tried one choice. One greedy choice was find me the smallest interval. And we know that that's wrong because we had this example by finding the smallest interval. Okay. Another choice could be find me the interval that begins first. Do you think that would work? Find me the interval that, I'll take the interval that begins first. First come, first serve. So I'll pick the first interval that begins. Will that work?
That might not be if you go on with a maximum interval.
Right. And there's a simple example, right? There could be one interval that's taking the entire time. And you pick that and you're in deep trouble. Okay. What other greedy choice can you do? Find the interval that ends first. Okay. So here is the let I interval that finishes first. That's our claim. Okay, this is the lemma we're going to prove. Given an instance, let the interval that finishes first, let that be called I. We are going to prove that it is part of an optimal solution. Okay? Notice that I'm not saying that it is in opt. I'm saying it is part of some optimal solution because there could be many optimal solutions. All I'm saying is it's part of some optimal solution. But that gives me the license to include it. I will include it, the remaining problem I will solve, and then I will move on. Okay? How do you prove it? So here is an instance. I is the interval that ends first. This is interval I. Every other interval, they could begin before it, but they are all going to end after. So, of course, there are a lot of intervals here. And there could be intervals that begin before, but they're all supposed to end. That's what the picture looks like. Okay? So we're going to prove that I belongs to an optimal solution. How do you prove it? All of these arguments where I'm trying to argue that something belongs to the optimal solution, the way we will argue is, we will say, okay, there could be many other optimal solutions. Give me any other optimal solution. Does it include I? If it includes I, then I'm done. Does it not? If it does not include I, then I'm going to make a change and include I and show you another optimal solution. Okay? So these are called exchange arguments. Let S be any optimal solution. Okay? If I belongs to S, then done. Right? We are trying to prove this statement. So we are considering the case where I does not belong to S. So suppose I does not belong to S. Then what do? I want to make some change to S so that I can add I to it and find a solution that has as many intervals as S has. What do? So we find an interval that finishes after S. So every interval in S finishes after S. Do you know that? Pardon?
The first interval that finishes.
So pick the first interval that finishes after S. Okay? And then?
We replace that by I.
Okay? Finish the first interval that. Okay? another way of thinking about it is, let me go ahead and add I to S. Okay? So add I to S. What happens when you add I to S? If it doesn't overlap, then what have I found?
The solution was not optimal.
I found a contradiction. Right? Why is that? S was supposed to be optimal and I've been able to add I to S. How can that be? Add I to S if S union I has no overlaps then contradiction. So I'm done in this case also. So I'm left with a case where there is an overlap. Okay, so what kind of overlap could it be? This is I. Here is a problem. Maybe it overlaps with multiple intervals. If it overlaps with 2 intervals, I'm adding I and I'm removing 2. That's a problem. So what do we have to argue? That it can only overlap with one interval. If I'm done, if you argue that you can only overlap with 1 interval, we are done. Right? Everybody see that? Okay. So how do you argue that it can only overlap with 1 interval?
Because it finishes
With
first.
Pardon?
It is finishing with I, like the bigger interval is finishing with.
Well, the bigger, so there are other intervals. So why can it not? So that let's pick any interval j that it overlaps with. So suppose j overlaps with I. Suppose I tell you that j overlaps with I, j prime also overlaps with I. Why can this not happen?
J will overlap with J prime.
Pardon?
And J will
Why is
overlap
that? Why?
Because I ends first, so they have to be.
Correct. So another way of saying this, if j overlaps with I, notice that j has to end after I. So if it overlaps, then this point should be inside j. Agree? This point also needs to be inside j prime. But how can you have the same point being in 2 different intervals? They were supposed to not overlap with each other. Right? So if j overlaps with I and j belongs to S, j prime overlaps with I, j prime also belongs to S, then this would imply that the finish point of I is in j and j prime. Implies j and j prime overlap, which is a contradiction because S was supposed to be the optimal solution, but does not overlap. So only one j that can overlap. So what do? You add I, remove j, and now you have a new solution that is as large as the optimal solution. So S minus j union I is also. Yes.
So is the J prime just a, is that an example of why I cannot overlap 2 different
Yes. So,
intervals?
yes. Correct. So let me do that. We're going to claim I does not overlap with 2 intervals. Claim I does not overlap with greater than 1 interval. The proof is by contradiction. Suppose there are two intervals j and j prime that overlap. That implies you have a contradiction. Okay? So to see, so I claim that we basically have the entire algorithm in place. Okay? We basically observe two things. One we observed is if somehow magically we are told, we are given a piece of the solution, optimal solution, we are given a particular interval of optimal solution, then we can go ahead and include it and solve the remaining problem. That's good. So now we have an iterative way of building them. But then we have to find a way of discovering this element of the optimal solution. Then we observed, oh, we tried some ideas. We tried looking at the interval, the smallest interval. We realized that the smallest interval has the problem that the first interval, the interval that finishes first, does not have, because there are two intervals that could overlap with the smallest interval. Right? That's basically the problem. While that problem is not there for the interval that finishes first. The interval that starts first also has a similar problem, and you can try to see that. So the key thing is, I would say there are two key things. One was sort of straightforward. The other was this greedy choice. The greedy choice tells us, gives me a way of isolating and identifying a particular element of the optimal solution. And now the algorithm is straightforward. Since I have to repeatedly find an interval that finishes first, what I will simply do is sort all intervals in order of in increasing order of finish times. For interval I, and then I go through all the intervals in that order. Set the initial solution to empty. For I in sorted order. Add I to S. Remove overlapping. Actually, maybe, yeah. Yes, let me write it. So for each I check to see if the start time of I is greater than the finish time of J. Okay, so that's the algorithm. I basically sort all the intervals in order of their finish time. Then I go through I initialize my set to empty. For each of these intervals, we go in that order. If we find that this interval starts after the previous interval that we added finished, then I can go ahead and add this. If it, I guess I could put greater than equal to if you're allowed to overlap the beginning. Doesn't matter. Here is the last interval I press. Yes.
So I'm just quite confused.
Yeah.
What if you had a scenario like the original case out there where with the two longer intervals and the one small one?
Yeah.
If that small one was the first interval, that still had an overlap with the first large one.
So
So you, one little one in the beginning.
here,
Yeah, there's overlap with that big one. And then there's one really long, yeah, same thing. So,
Okay.
I'm just confused how that would.
so what would we do? You would pick this one first, you would remove this, and then you would pick this one. So you would get 2. And that's the best you can do.
But that's not optimal. Would it be optimal to take 2 longer ones?
No, no. So what are we trying, what is our objective? It's just the number of intervals, not the time we are trying to fill. Okay? And that's a different problem. You could say, I want to schedule the largest, the intervals that take the most, that use the room the maximum or something like that. That's not what we're looking at. It's just a sheer number.
Okay, so we don't know which intervals, we just know the count.
No, we know the intervals. We only care about the count.
The output.
The objective is just the count. Okay? Yeah.
What does it mean, interval finish first?
Finish. This is the finish time. This is the start time. So this is time. Okay. So this is time. Maybe this is time 1. This might be time 3. This is time 2. This might be time 7, 8. Okay. Any other questions? Is the algorithm clear? You're basically done. That's the algorithm. What's the running time of the algorithm? If you have n intervals, how long does it take to sort? N log n. Empty. We are just going through in sorted order. We can just keep track of the last one that we added. So this is just a constant amount of time. So it's just n log n. It's just sorting. Okay? Yeah.
If you are given a sorted interval, will it be n?
If we are given the entire sequence in sorted order of their finish times, then it will be just n. Yeah.
How will the first item be added?
Good question. So I guess we assume that the finish time, there is nothing added, so we just go ahead and add it. Maybe I should say that. If S is empty or okay. Yes.
How do you know which interval is the last interval to be added?
You can just keep track of it when you add this. So if you want to be really precise, then let's do this. So let me. I'm going to make some changes. So you keep track of a time. Let's call it f. Let's call it t. Initially t is 0. And you say if your start time of I is greater than 0, greater than t, and when you add I, then you set t to be f of. Okay, what is t? T is the time when the last interval finished, the previous interval finished. Okay? We initially set it to 0. And assume that all intervals begin after 0. Then whenever you add an interval, you go ahead and set its finish time. You set your t to be its finish time, because you're not supposed to add any intervals before it finishes. So you're only going to look at intervals that begin after t. So this whole thing is just linear time. Once you have sorted, the whole thing is just yeah.
If there were weights to intervals,
Yes.
How would we treat the
Good,
grading?
very good question. So what happens? In fact, it's a more realistic problem. We might be getting money for each of these, so there might be a dollar value associated with it. So it might be that some smaller intervals might give us a lot of money, and some larger intervals may or may not give us money. So we proved two things. We proved this greedy choice, and we also proved that fairly straightforward statement that if you somehow find something, then the remaining problem, you just take it out, remove overlaps, and solve the remaining problem. One of these two statements still continues to be true. Which one is it? That one. If you can somehow identify one thing, then the remaining problem is very clear what you need to do. This one is of course not clear. It's not true, right? You can easily come up with examples. Yeah, you can come up with tons of examples. Maybe the first interval that finishes first, the interval that finishes first gives you no value. Then why would you pick it? So one question is there a different greedy choice property you could do? Okay. Can you think of a different greedy choice property in that case?
We can sort by the weights.
Sort by weights, and then pick the largest weight. You can think of easy examples that will foil that. Maybe the one that has largest weight is huge, and the others just have slightly less weight, and you are getting rid of all of that. Okay. It turns out no greedy choice will work. So we are going to use a technique called dynamic programming to solve that, which still requires something like that. So we'll cover that in subsequent classes. Yes?
Sorry, can you explain one more time what f of I is?
F is the time at which the interval finishes. Okay? So let's say this is an instance. Okay? So this is time is given. It's going left to right. Okay? So let's say this is 1. Let's say this is time 2. This is time 4. This is time 6. Time 8. Time 9. 10, 11, 12, 13, 14.
Oh.
Okay, so if this is the interval I, then S of I is 4, Fi is 9. Okay? Any other questions? Yes?
Where it says where J is the last.
So we don't need it.
That's not even needed. Sorry. Once I add this. Okay. Thank you. Okay. I made the algorithm more precise based on that. All right. Any other questions? Okay. So, so that's one example. Let's do another, in my opinion, much more interesting example of 3D algorithms, and that is problem from compression, from data compression, also comes up in coding theory as to how to represent large data files most efficiently. So let's say you're given a data set, a large file. Let's say it has around 100,000 characters. Okay? It has 100,000 characters, but to make our life simple for now, let's assume that these 100,000 characters are all drawn from this alphabet. Okay? 6 letters. They're all drawn from this. So, what you are further told about this large file is that so they appear in certain proportions. So the frequency of A, you're given the frequency for every letter. So you're given frequencies, let's say E appears 50% of the time, A appears 25% of the time, T appears 10% of the time, D appears 9% of the time. Okay, so the actual numbers don't matter. It's just the relative numbers matter, and I'm just 50, 25, 75, 85, 94, 98. Okay, so that's the frequency that they appear. So in particular, 50,000 of these characters are E. Okay? So you know this. So you are trying to transmit this file using some technology, and you want to send it to somebody else, but you want to use the minimum possible amount of bandwidth to send it. Well, we all know that characters are nothing but bits, right? So, but we have to distinguish between them, between these 6 characters. So I could simply use bits to write them. How many bits would I need to distinguish between these 6 characters? I would need at least 3 bits, right? So what I would do is what is sometimes called a fixed length encoding, which is what you do with ASCII characters and so on. Where I simply say, okay, A equals 0, 0, 0, B equals 0, 0, 1, C equals 0, 1, 0, D equals 0, 1, 1, E equals 1, 0, 0, equals. Okay? That's a clean encoding. You agree that encoding and decoding is very straightforward. Whenever I see an A, I replace it by 0, 0, 0. Whenever I see an E, I replace it by 1, 0, 0. And how do I decode? I again do a linear pass. I do 3 characters, 3 bits at a time. And from those 3 bits, I have a lookup table and I look it up and figure it out. Very straightforward. Linear time encoding, linear time decoding. We are going to be worrying about the time it takes to encode and decode, but our crucial question is how many characters, how many bits are we using? So how many bits are we using to represent this file? 300,000. So that's our size. Okay? Now, obviously, you notice that this is a little bit of a bad thing to do because E appears so often that you might want to reserve far fewer bits for E. Right? So you might try to say, let me be smarter about it. Instead, let me use a variable length approach. So in the variable length encoding, you are not forcing yourself to use the same number of bits for every character. So you could say, all right, E is the most common character, so let me just use 1 bit for that. Then the next most common character is A. Let me also use only 1 bit for that. Then I have D. I use these 2. Then I have after DB 1. Then I have C. I could try something like that. This is sort of the obvious thing to do, so that I give the smallest number of bits to the most frequent character. But there's a serious problem with this, right? What's the problem? So I can certainly encode it. Encoding is straightforward, but decoding would be hell, right? Because how do I tell when I see a 0, is this an E or is it the beginning of a T? It's impossible to decode. Okay? So then the idea is, all right, can you do something else? And this is the notion of what is called a prefix free code. It's also sometimes referred to as a prefix code. Okay? It's a code where you make sure that whenever no code for a character is the prefix of another code, so that there will never be ambiguity. Whenever you're seeing something, if it has not yet been decoded, it can't be. If it is not, either it's not been decoded, in which case you keep decoding it, or if it is decoded, then this is the unique way of describing it. Okay? The way you describe prefix-free codes is using a binary tree. Okay, so let me just take that. So here is one thing you could do. You could say E is really the most frequent character, so I'm going to just give one bit for that. But once I have chosen only 1 bit for E, I cannot give anybody else a code starting with 0 because it has to be prefix free. Okay? So what do you do the next one? Let's say A has to start with 1. But if I just do 1, then I'm in trouble because then I'll have no more codes left. So for A, I will do, let's say, 1 followed by 0. That means nobody can start with 1, 0. Then let's say I do D next, D and D. For D, I could say has to start with 1, 1. And I could say D is 1, 1, 0. Then I have B has to start with 1, 1, 1. And so I can do 1, 1, 1, 0. And then I'm left with E and F. Sorry, not E and F, C and F. C could be 1, 1, 1, 1, 0. F could be 1, 1, 1. Okay? Any questions? So, this is just an attempt. Let's see whether we make any progress using this. So, what will the size of the file be? Well, for 50% of the characters, it's just 1 bit. So 50 times 1. For 25, it's just 2 bits. 25 times 2. For 10 of them, it is 3 bits. 10 times 3. For 9, it is 4 bits. 9 times 4. For the remaining 6, it is 5 bits. 6 times 5. Okay? So 50 plus 50 is 100. 130. 160.
196.
196,000. nearly 30% or more improvement. Okay? So clearly significant improvement. Now notice that the thing is I have encoded it. For the other side to decode it, they have to know this association. Okay, how are they going to figure out this association? They do not know. So I have to send this association to them. So this association can be sent by the following tree. I have this key sitting here, indicating that's 0. So it's a binary tree. The left branch indicates a 0, the right branch indicates a 1. So I have an E, 1, then I have a 0, 1, then I have a 0 here, then I have a 1. Maybe I should draw somewhere else. Okay, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, E, A, E, A, D, B. Okay, so that is called a prefix code, the prefix tree, whatever. This is the code. So when I send out, I will send the file out along with this. Now this is only a small amount of stuff. It's just 6 characters, right? This is a very, very, very small file. So it's very straightforward to send it. And then decoding is very straightforward. What do you do for decoding? You read, you start from here, and you keep reading. If you read a 1, you go here. If you read another 1, you go here. If you read a 0, you go here and mark that as a D. Then you go back. And that's it. It's just linear time. Very, very simple decoding. Okay? So this begs the following question. For this file, is that the best prefix code? Okay? What is the best prefix code for a given file? That's the question. And that's exactly the problem that Hoffman set out to solve. And he came up with this really elegant and something that we'll completely understand and prove algorithm called Huffman codes, which are widely used in communication, as well as in coding theory, in digital compression, and so on. All right, so let's take the problem more precisely. What you're given is a series of letters in an alphabet, and you're given frequencies. And your goal is to find out the prefix code that gives the best encoding, that encodes, that compresses the file most. Okay, so here's the problem. Given an alphabet A with frequencies F. Okay, so F of X will give you the frequency for X. Given prefix code. By the way, I'm using the term prefix code, the technical term prefix free, prefix code, they're both used. Okay, I'm just calling it prefix code. Prefix code of minimum cost. What is the cost of a prefix code? Well, the cost of a prefix code is the way we specify a prefix code is what? By a tree. Okay. So the cost of the prefix code will be given by the cost of the tree. I will add over all characters in the alphabet. I will multiply the frequency of the character with what? With the depth of the character. Every character will be a leaf. Depth of the character in the tree. So times, I'm going to use this notation. Okay, so this is the depth of x in t. So I need to find that t that minimizes this. There are many ways in which I can arrange the leaves. Many ways in which I can construct the tree. Many ways in which I can arrange the leaves for a given tree. I need to find that tree that minimizes this cost. Okay? Is the question clear? Alright? And we are going to show that there is really a beautiful greedy algorithm. Not very straightforward. It has some very sort of elegant ways of looking at it that will give us guaranteed the best solution. Okay, so one of the things we observed with this example was, let's say E was at the, has to be at the top. Was one of the, E was the most frequent, so we really put that as high as possible. So let's try to make some observations about this optimal solution. Okay? So suppose, so that's one of the main things you have to try to understand when you're trying to do, trying to solve some optimization problems. Before even coming up with ideas for the algorithm, think about what the optimal solution would look like. Come up with some principles for the optimal solution. So let's try to understand, let's say P star is the optimal P. Let's try to understand the structure of P star. What principles can you, what observations can you make about T star? Remember, T star is sum. We don't know what it looks like. Okay, I've drawn some tree like this. If you look at the details of this tree, do you think this is an optimal tree? I haven't given you more information about it. All the leaves are sitting here. Do you think this could be an optimal tree?
No.
Why is that? Can you raise your hand? Why can this not be an optimal tree? Yes?
The depth on one side is higher than the other, so it's kind of a bit unbalanced.
Well, but look at this tree. This is maybe a very good tree. And if you have a very skewed input, where some input has very high frequency compared to the others, it may make sense to keep things skewed. Yes?
There is no leaf node at every level.
There is no leaf node at every level. Well, certainly there are leaf nodes. That's not. There are cases where, for example, let's suppose we had 4 characters, all equally likely. What would you do? What would be the best tree there?
Balance.
It will be a completely balanced tree, so all the leaves will be at the lowest level. So it's not necessary to have leaves at every level. Yeah?
You could just remove the last node and that would be better than this, irrespective of the frequency.
Very good. So this seems like a completely useless thing to do. Right? I could just remove this node and move this up. You agree? So what else can you say? There's one other problem. So let me fix that first. There is one other problem with this tree. Yeah?
It's like in that same subtree.
Yeah.
That node right there.
Yeah. That can be moved up. Okay, without any more information, I can't say anything more. This could be an optimal tree. Okay? But this is what, so first thing you observe is that the optimal tree has to be, this is what it's called, I don't know what the technical term for it is, it's called a full binary tree. That is, you would never have, so this is a full, yeah. So the definition is, every internal node has to have two children. No internal node will only have one child. Because if internal node had a one child, you could just move it. Okay? Every internal node so that's a great observation. That's observation number one. Okay, now let me put some characters here. Let's say this is A, B, C, D, E, F, G, H. What can you say now about these characters? If this is really this optimal solution for these characters, what can you say about these characters? Yeah.
A and D will be the subring.
So A and D are the ones that have the highest frequencies. So A has one of these two we do not know. Okay. What else can you say?
The last two
These all are the same height, right? 1, 2, 3, 4. All of these. So in general, can you say that more succinctly? What we're saying that the depths should be inversely proportional, in the inverse order of their heights, right? So if f of x is greater than or equal to f of y, then what can you say? D t star of x should be less than or equal to. No controversies about that, right? And you can prove it by looking at the cost. Okay, how do you prove something like this? If it was not, what do you do? So how do you prove that statement if you have to prove this? Well, if d of t star x was greater than d of t star y, then you look at the cost and you just swap those two. Then in the cost there will be two terms, right? In one term you're adding, let's actually do this formally. So cost of consider t star with x and y swap. Okay, just one second. What's happening? In t star, our cost, what are we paying in t star? We are paying dt star x times fx plus dt star y times fy. That's what we were paying. And there is of course other things we are paying, but I'm just looking at what we are paying for these two. What about in the new tree? What are we paying in the new tree? Yeah. dt star x times fy plus plus dt star y times fx. Agree? I want to show that this is smaller than this, right? To show that this is smaller than this, I could subtract this from this and show that that is greater than 0. Okay? So I will subtract these two, and what do I get when I subtract these two? I get d. You know that. So suppose for contradiction, dt star x is greater than dt star y. Okay, so dt star x is greater than dt star y. So I'm going to add these two. So then the difference. So let me say this is a, this is b. So I'm calculating a minus b. So a minus b is dt star x times f of x dt star minus dt star y into f of x plus dt star y minus dt star x into f of y. This is equal to f of x minus f of y times dt star x minus dt star y. And both of these are non-negative. This is non-negative, this is non-negative. So this is greater than or equal to 0. So T star and the new tree, if T star's cost is at least the cost of the new tree, so I can do the swap and guarantee and still maintain an optimal solution. Okay? You have a question? Yeah.
Which tree are we still in the assumption we're only using zeros? We're only using binary to
Yes.
decode?
Yes. So this is 0, 0, 1, 1, 0, 0, 0.
So if it's not structured like the example you have above,
Yeah.
if I send over, let's say, encoding that 0, 0,
Yeah.
how do you know that's A versus just two occurrences of whenever A's parent is?
No, there is nothing here. The only characters are sitting here. The characters are only at the leaves. Very critical. Okay. Any other questions? Good. So that's a very crucial observation. Okay. The problem though is it tells me what order, but notice that there is too many. It tells me that the highest ones, the highest frequency should be high up, the lowest frequency should be low. Okay? But because of the fact that these are not holding any characters, it's very difficult to split the characters into two parts. It's very difficult to see that, oh, these two are the biggest, so I'm going to set them aside. These are all smaller, I'm going to set them aside. That seems difficult to order. So what we're going to argue is the following. The key property we're going to use so we're going to use two key properties. I'm going to write that. So, two key properties. Something similar to what we argued before. let's say no, sorry, and the greedy. Okay. So let's say we did the following. We have observed that the depths are in reverse order of their frequencies. So the one thing we're going to prove is the following. Suppose alpha and beta are the two lowest frequency characters. Okay. Then there exists an optimal tree that looks like this. Okay, the tree, there are lots of things going on in the tree. I don't know what's going on here. I don't know what's going on here. But at the lowest level, alpha and beta are siblings and have a okay. There might be other things at the same level, but alpha and beta are two siblings at the lowest level. There exists an optimal tree in which alpha and beta are siblings. You agree that this part is consistent with what we are observing there, okay? Except that I'm putting more condition. I'm even saying that they are siblings. So you look at alpha and beta; they are the smallest frequency elements. So we are going to argue that alpha and beta are siblings sitting at the lowest level. So we're going to prove this. Let's suppose I am able to establish this. Then what do I do after that? Okay, remember, in the interval scheduling problem, we identified a particular interval. What did we do? We just picked it and solved the remaining problem. If I identified that alpha, beta are these characters that can be viewed as siblings, okay, what do I consider as my remaining problem? Well, so alpha and beta, so what we're going to argue, and this is a little bit of a tricky observation, but if this is the picture that looks like, so alpha and beta are sitting somewhere there, and let's say alpha beta's parent does not have a character, right? Because the characters are only these. So let's say this is my T star, okay? Then if this is optimal, we are going to claim that the following, which looks identical to that, except that instead I'm going to remove this whole thing and replace it by a new leaf. Let me call it gamma, okay, whose frequency is going to be the frequency of the sum of alpha and beta. We are going to argue that the remaining problem is the same as the problem in which we replace alpha and beta replace everywhere alpha and beta with gamma. And gamma's frequency will now become the frequency of alpha plus beta. And we solve that problem. Once we solve that problem, we can just remove the gamma and replace that with alpha and beta, and there is a solution. So we're going to prove two things. We're going to prove one, that the greedy choice, that if alpha and beta are the two lowest frequency, then there is a solution in which alpha and beta are actually siblings. Then once you identify that, you will say, then my remaining problem is, I'm going to view alpha and beta as just one character gamma, whose frequency is the sum of alpha and beta. And then once I solve for that, I will get a solution for that, but then I will replace the gamma by a node with alpha and beta as its children, and that would be my solution. Okay? So in particular, I don't have the previous, I think we are running out of time. I do want to give out the exam. So we will go over the running of this algorithm, and we'll prove these two next class. Okay, so before I hand out the exam, let me say a few things about it. Okay, so I'll just say a few things based on grading. So we went the stable matching. Most people got the initial parts correct. There was one question about the proof, which was basically saying that if Gale-Shapley's, where you start with man proposing, returns the same stable matching as Gale-Shapley where woman is proposing, then you need to prove that there exists, that the stable matching is unique. Okay. A small number of people misunderstood the question. They said, oh, stable matchings need not be unique. But the people who tried to prove it, they were, I think many of you got it right, many of you did not, got it partially right. The most common mistake I noticed was that arguments, something to the effect saying that if this is if Gale-Shapley man is Gale-Shapley woman, then every woman gets their most preferred man, and every woman gets their most preferred woman. That's not true. Okay. When we say man optimal and woman optimal, which is what you have to end up using, what we mean is every man gets the woman, the best woman they could possibly get in any stable matching. So if these two matchings are the same, then if M is matched to W, then W is the best possible solution for M among all stable matchings. W may not be the most preferred woman for man. Okay? So if there was, so let's say this is our stable matching S that we get from here. Let's suppose there was another stable matching S prime in which man M was matched to somebody else, let's say woman W prime. Then the woman W must also be matched to somebody else and prime. But since this solution is man optimal, W is most preferred M among all stable matchings, including this one, which is supposed to be a stable matching. So that means W is more preferred than W prime. It's not the case that W is most preferred. All it says is W is more preferred than W prime. Similarly, since this is also woman optimal, M is more preferred than and prime. So therefore there is an instability here. So that's basically. So you need to write this, and this, and you get instability. Many people try to give examples. That okay, let's look at this example with 3 men, 3 women, 2 men, 2 women. None of those are proofs. Okay, so again, it's good to work with examples, but putting examples down as proofs are not. Okay, asymptotic notation. There was a question basically about comparing functions. So it was you're given f of n and g of n, and you're supposed to compare f of n to the power of 1/3 with g of n to the power of 1/3 or 1/4, and I think it's just following the definition of asymptotic notation that you can use limits or you can use the c and 0 and then try to give a counterexample or a proof in that case. We'll post solutions to this. Many people got the recurrence right. Basically it was e of n is 9t/3 plus square. Many people use master theorem, which is fine. Many people use the recursion tree, which is all fine. But there were the mistakes that people made. There were several cases where people missed the log n. And occasionally that was, I would say, the most common mistake. Okay, analysis of the sorting algorithm. This was a weird sorting algorithm that basically first it did a swap of ai and aj, and then it looked at this. Then it made a recursive call to the first 2/3. It made a recursive call to the second 2/3, and then it again made a recursive call to the first 2/3. Okay. So first thing was the recurrence. Notice that the only step that was not recursive was the swap. So there is only a constant amount of time being done outside the recursion. Okay. So if you're trying to solve for t of n, you're doing some one amount of work, some constant amount of work. But then there are 3 calls to 2/3. So this is the recurrence. Okay? You can solve it using master theorem or recursion tree approach. The proof, many people did not get the proof argument as to why this algorithm sorts. And the key thing is, I think one of the things in a recursive algorithm, it's really the recursive steps should be very, very carefully looked at. A lot of people try to argue, oh, since you're doing a swap, you will eventually do enough swaps to sort. But that's not that's not what's going on. What's going on is the fact that this swap is actually only for the base case, even though it's doing something other times. But the only reason this swap is there is for the base case. If you're left with 2 elements, you go ahead and swap the 2 elements. That's the main reason for this swap. Other than that, what you're doing the first 2/3, then you're doing the second 2/3, then you're doing the first 2/3 again. So this, the best way to argue is using induction, that if you did the first 2/3 correctly, then in the first 2/3, the larger half is here and the smaller half is here. That means when you do the second 2/3, okay, so when you sort the second 2/3, all the elements that could possibly should have ended here are on this side, and you're sorting on those. And then you argue that by the end, this should contain all the largest 1/3. And once you have shown that this has the largest 1/3, you're done, right? Because you're sorting this whole thing anyway. So that was an induction argument. Okay? Local minima, local maxima. The basic question was, there are some issues with some students. What if I don't find the local minima or local maxima? But notice that we observe that the global minima is also a local minima. So there is no issue of there not being a local minima. There always is a local minima. And basic idea was using binary search, and you just have to be careful with what's happening in the middle of the binary search. So if you have to find the local minima, you look at the middle element, let's say, and you look at split into two parts, and you check whether any of these two could constitute as the local minima, which you can check because all you have to do is compare with your neighbors. And based on that, you can decide which direction you have to go to. And that was a log n time algorithm. You could, of course, also do linear time by just finding the global minima and return it. That's a valid solution, but it's not as efficient as this. Okay. So we'll hand out this statistics here. So so the way bonus points are, one of the questions was a bonus question. So the way always bonus points will be treated is, if you have not done it, you will never be penalized. If you have done it, it will only increase your grade. Okay. So whenever I give statistics, it will be not counting the bonus. Okay. So the median score was 23 out of 30. Max was 20. And for what it's worth, we look at standard deviation was approximately 4.5. So the way you should interpret these grades, roughly speaking, the median grade is about a B+. Okay. So this is about a B+. Again, the grades are going to be based on the entire scores, not just this, but just to give you a sense of what it is. 27 would correspond to an A, and if you go down to 19, that would correspond to B minus, roughly speaking. We will try to post your total, you calculate totals and post it. Okay, so
证明那个证明后我不会修好。
I'm going to put, handing out a problem. So I'm going to put so they're all sorted by first name. They're all sorted by first name. So I'm going to put A, B, C, D. So please put it back right there. This is all first name.
हाँ तो वेंसडे को तो आना पड़ेगा आज है बोनस बोनस I'm sure बहुत
I want to find how hard this grade is going to be. I could just wait until I get make probably 6 and 7 weeks.
Yeah, for flashback yeah, that's horrible.
The world was so obviously heavily every time I watch you. I guess it's supposed to.
Oh yeah, for restaurants.
Yeah.
Wasn't the last one like, were they playing like Houston? Yeah, it's not by that, but they were fine. This stayed up last until 1. It took me the last 2 days.
Starting, we were on the start games at like 10, 11 at the time. The Dodgers. It's gonna be rough.
Yeah, I'm just kind of freaked out right now.
Yeah, like a 4.5 is a huge 10. So I feel like I'm getting screwed. But a 65 is for me with maybe B minus.
Yeah.
Wait, what's the B? What do you have? B minus 19 out of 30 is a B minus. Yeah, 65% is a B minus. Even if you did 65% bad, then you would have a B minus.
No one else has it.
First name Pete.
Like with all the people celebrating.
First name Q. First name R. Can you please put it back once you're Q? First name F. There's more coming. Can you please keep the speech back? First name F. There's more coming.
I don't know, man. All I know is just like, wait, first name R. The stack of the first name W.
First name F.
I don't know, but ours is over there.
They're all sorted.
Matt! You're just over here.
That's all first name F. Just leave them sorted.
Yeah, it's completely anonymous, don't worry.
Where?
I want to know what exactly what you say. You already finished it. I didn't drop the box. 1, 2, 3.
I was expecting 15.
First name.
My entire recognition is wrong, but
Honestly, I'll give it up.
What are you looking at? No, first name.
Like initial answers for certain things. I started saving initial answers on You got this. It's 1 minute.
No, not yet. It will be posted. We post the solution. Post the detail. If you have questions, you can
You already used
So it's a 2.2